I just have to look at the book. It's freestyle. Oh, it's going to be freestyle from now on.
Freestyle video.
Cat? Maybe just rap videos.
Yeah, that was it. How to balance my checkbook without being, I didn't in high school.
I don't know how to balance checkbooks.
What?
Really? All right. So the key ideas are you'll have an equation with an x and a y where y is not necessarily by itself, and if it is, then that's great. If it's not, then but identifying the distinguishing features for a parabola. You got x is squared, y is not squared. So when you see an equation relation between x and y, and you see that x is squared and y is not squared, you got to think this is a parabola, right? Not only that, it's a parabola going up or down. And that's a little bit different when x is not squared, but y is. And then so in those cases, those are parabolas going sideways. So that's the general way to pick it out without doing much work in the beginning, so you know kind of like what to anticipate. So for an ellipse and a hyperbola, both x and y are squared. Both x and y are squared. And when they're both squared, it doesn't matter which side they're on, but ideally you want everything, all the variables on one side, so that you can start identifying this a little bit better. So when both x and y are squared, you either have an ellipse or a hyperbola. Or really, a circle. I'll put that under ellipse. So an ellipse, both x and y are squared, and the square terms have the same sign. And if both the square terms have the same sign, then you have an ellipse. And you can go even further. If the square terms have the same sign and same coefficient, if they also have same coefficient, then we have a circle. Okay? Otherwise, it'll be some sort of ellipse, and it'll be up to you to figure out after you complete the square and do all that stuff. Try to figure out its major axis and minor axis and which way it's elongated and stuff like that. If the square terms have different signs, then it's a hyperbola. And if they have different signs, one of them is going to be negative, one of them is going to be positive. Now, I was going to put down if the x is negative, then it's going to go sideways or something. It's either going to go sideways or it's going to go up and down. But it kind of depends on the constant on the other side. Like, for example, if I have x squared minus y squared is equal to 1, then kind of use your logic to try to figure out which way it's going, right? So I'd like to think about it is that if x is equal to 0, that's somewhere along the y-axis, right? When x is equal to 0. If x is equal to 0, then y is equal to 1. Actually, if x is equal to 0, then this will never equal to 1, right? So x is equal to 0, or the y-axis, will never exist, so this would be opening up sideways. But I know this isn't the form of your hyperbola, but sometimes when before you finish all your work, you might be at this point before you divide out a -1. And in this case, if x is equal to 0, then this could still be true. So you have to be careful about how you want to set up. I guess the bottom line is that if you get the right-hand side to be equal to 1, the sign of whatever's there, the negative sign is going to be the axis that this is not going to go up and down on. Does that make sense? So let me rewrite this last one as negative x squared plus y squared is equal to positive 1. And as long as you have this positive 1, then you can say the graph is not going to exist when x is equal to 0. I'm sorry, when y is equal to 0 in this case. So y is equal to 0 as the x-axis, so it's going to have to exist on the y-axis. And then you know that box that we did yesterday, that'll help you find your asymptotes and stuff. I don't know if that got all confusing. Maybe if I change the color of... This isn't really part of the graph, but it's part of what helps you draw your hyperbola. Okay. All right, so I think that's a quick rundown summary of being able to identify your conic sections. And I think it's good practice to do this. Because later on, we're going to take these conic sections to a higher dimension. And what we're going to do is we're going to start looking at what's called quartic surfaces. And they're like three-dimensional versions of these things. Ellipsoids and paraboloids and hyperboloids. Sounds cool, huh? Hyperboloids, paraboloids, and ellipsoids. And the circle would correspond to a sphere in 3 dimensions. Okay. So that's a rundown of the last couple of lectures that we've been looking at. And today what we want to do is we want to tie in the conic sections with the polar coordinate functions, and then from there maybe look at it from a parametric point of view as well. So today, relationships between conic sections, polar graphs, and parametric equations. And so maybe we might be able to plot the path of the Earth around the sun. Do you guys know what figure that makes, the path of the Earth around the sun? It's an ellipse, right? People thought it was a circle for a long time, and then Copernicus, I think he was the guy that figured it was an ellipse. Anybody know if it was him or somebody else? Kepler. Yes, it was Kepler. Copernicus. Who's Copernicus? Did you just make that up?
He's the guy that Galileo messed up. Yeah.
Oh. Okay. So, like I said, I don't have notes, so I'm just going to copy from the book. And we'll try to dig out some examples and stuff like that. So let's take a look at this theorem that's in your book. And let's relate it to at least an ellipse. And I don't know if I want to talk too much about hyperbolas and parabolas, but let's imagine this idea. We have F is a fixed point called a focus, and we've studied focus points already. And I is a fixed line called the directrix. So that sounds like we're dealing with a parabola. Let E be a fixed positive number called the eccentricity, and then set all the points P in the plane such that the distance from the point, some random point, to the focus point, and the distance between the point to the line is a fixed number, which is the eccentricity. I guess since we've dealt with fixing a point and finding distances from the focus to a point and the point to the directrix, maybe we should talk about a parabola first. So we're looking at the ratio between them, and the ratio, they want the ratio to be constant. And so if the ratio is constant, then depending on what E is equal to, or depending on what this fraction is, that's going to define what kind of shape your graph is. So let's take a look at a parabola. And again, we're not going to study parabolas too much in terms of eccentricities and stuff like that. But we'd like to know that we can if we really need to. So with a parabola, this whole setup seems like it's set up for a parabola. We have a focus, and we have a directrix. And then if we pick a random point in space, and then the distance between the focus and the directrix, let's call this P, and then this is PF, the distance, and this is PL, the distance. If those two distances are the same, they're equal, then the ratio of them is equal to 1, right? And so that means if we pick another point over here, another P, let's call it P1, where we find the distance between P1 and F, and then the distance between P1 and L. And again, if those distances are the same, then this point P1 belongs with our set of points that make this parabola. Okay? So in terms of the eccentricity, if the eccentricity is 1, then we got ourselves our parabola. All right, let's jump to the ellipse picture now and see if we can get an idea of how this thing might look like. Again, we'll start off with a line we'll call L and a point that we'll call F. And so let's fix an eccentricity to be, we want a number that's less than 1. Let's pick 1/2. That seems to be easy. Let's say E is equal to 1/2 here. So that means the distance from the point to the line should be twice as big as the distance from the point to the focus. So let me go right between them, and the distance between the point and the line this is P here, should be twice as big as the distance from the point to the focus. All right. So if I imagine, it's hard to imagine this, it's not moving, but if I imagine another point over here with that same sort of scenario, I can pick another point over here maybe. I don't know if that's twice as long. 1, 2, maybe. Maybe that's too long. Should have written a program that does this for me. That looks about half. So this is, let's call this P1. So the distance between P1 and the line, and the distance between P1 and the point. So the distance between P1 and the point looks like it might be half of the distance between P1 and the line. That makes that ratio equal to 1/2. I guess a more interesting point would be to look at a point that would be, let's say, I'm going to do this in red just so it's a different, or maybe green. I'll do this in green so that it's a different color. So the distance between the point, and if I double this distance over here, 1, 2, I could be over here in this point. Let's call this P2. And the distance between P2 and the line is about twice. Is that twice? That's not twice. Maybe I need to put my point over here. Oh, I made this dot like 7 times. So the distance between point P2 and L is twice the distance as the distance between P2 and F. Maybe I'll do one more over here. So somewhere over here, the distance between this point, let's call this point P3, the distance between P3 and L is twice the distance between P3 and the point. So anyways, we've collected a few points over here, kind of random points. And if we follow those random points around, we have ourselves an ellipse. Okay, so if we keep that ratio between the distance between some point and the focus point and some point in some directrix, then we have our eccentricity. Okay? So if you could sit down and try to imagine what would happen with a hyperbola, then that would be okay. So this is something that we didn't talk about before. We talked about a directrix for the parabola. That kind of made sense because that's how it was defined. But we didn't talk about a directrix for an ellipse or a hyperbola for that matter. Apparently hyperbolas have directrixes as well. So now we can refer to the directrix as that line that helps you find the ratio of distances. Okay? So that's eccentricity. It turns out that when you talk about bodies orbiting something else, whether you're talking about the Earth going around the sun or satellites that are orbiting the Earth, the moon going around the Earth, it's always referred to with an eccentricity. And these are the ellipses that we're talking about. So when the eccentricity becomes 1, this thing breaks off and it doesn't follow an elliptical curve anymore, which means it flies off the orbit, so it's no longer orbiting around. So that's why the eccentricity is important, because if the eccentricity is close to 1, we know that it's almost breaking off. Those comets, the Halley's Comet, they go around the sun, don't they? So those Halley's Comet that go around the sun have eccentricities that are very close to 1. And it turns out that an eccentricity close to 0 can anybody guess what that would be? If you have an eccentricity that's actually equal to 0? You actually have a circle. And so our orbit around the sun turns out to be an eccentricity that's really close to 0. Because our path is almost circular. It's not, but it's almost. Okay, so that's a business about eccentricities. So it turns out that with these eccentricities, you can define the shape of your conic section. And once you define your shape of the conic section, you can easily transform this into polar form functions. They don't say what D is, so we have to go back and talk about D for a minute. So they don't say what D is. I mean, they do. They show pictures of it. Let's just mention what D is equal to. So a polar equation of the form R is equal to E times D divided by 1, and then there's a plus or minus E times cosine theta. And the denominator represents a conic section with eccentricity E. And the conic section is an ellipse. If E is less than 1, it's a parabola. If E is bigger than 1, and if it's a hyperbola if E is bigger than 0. And D, by the way, is a directrix. That comes from the equation of the directrix. And the directrix is it's either a horizontal or vertical line. But what we want to look at, the way we want to look at this is that it's a constant value. It's a constant value that describes the directrix. So depending on what your equation is. So for example, if we have, trying to think of the standard parabola, 1/4 or 4a or something. I'll take a guess, and if it's wrong, it's wrong. Let's say your focus let's just say your directrix. Your directrix is y equals to negative 4 or 1/4. 4. Let's try 4. No, let's put 1/4. And let's have our e to equal to 1, so we know it's a parabola. So what we could do is we could take a look at the graph of this. R is equal to e is equal to 1 times the directrix 1/4 divided by 1, and it says plus or minus. Let's I'm going to take a guess and have it as a plus, and then we'll take a look at the graph. I want the graph to be your standard y is equal to x squared parabola. Let's see how that turns out. And I'll use the cosine function. So let me take out my graphing calculator program. And graph this polar coordinate function. Doesn't get smaller. Okay, so R is equal to negative 1/4 divided by 1 plus cosine theta. Uh-oh. That went sideways. Oh, I need to use a sign. Ah, it didn't go to 0. Oh well. So this is the graph that we're looking at. So this goes to 1/8, and oh, theta is 1 point. What's 1.5 in angles? 1.5 radians is about what? .57 actually. Pi over 2? That sounds like pi over 2, right? 3.14, 1.57, pi over 2. So it is pi over 2. So let's change this to sine, and then we get this parabola that goes down like that. Okay. By the way, now that I look at this a little bit more carefully, the focus point that we're looking at is actually at 0, 0. So I couldn't have been able to draw that y is equal to the x squared parabola because of the focus point. Yeah, these are equations of focus points at 0, 0. So let's take a look at like different families of these things and see what we can gather from these equations and the equations that we're seeing them being graphed. So I'm going to do a big screen on this and change some parameters here. So I'm going to say there's two numbers that we're multiplying, the eccentricity and the directrix. And let's make the directrix equal to 1. And then the eccentricity also goes here as a coefficient, I think, right? It's E times D, and then 1 plus the sine. So an interesting thing to do is try to take a look at families of curves to see what happens when you change the eccentricity or the directrix. So let's call this directrix D, because we can. And let's also graph y is equal to D. And then we'll let D equal to a few different values. So when D is equal to -2, we're down here, and that's a parabola going up. And when D changes, when D gets closer and closer, in this case D is equal to 1, so this is the graph that we had, it looks like it goes through positive and -1 in the x-axis. So a more interesting thing that would happen is that if it goes to 0, right at 0, it just kind of, when D is equal to 0, I just have R is equal to 0, so I don't have a graph there. But when it becomes positive, you see that it turns back around. It goes upside down. So these are all parabolas, and then they change the order. So we have plus or minus in the denominator. So what if we change this into minus? What do you think will happen? Sideways? No. Your directrix is in the wrong place, it looks like. I don't usually like messing around with negative signs with these things. All right, let's change from sine to a cosine. We already saw what happens there. I think I had a cosine on first. And if we had a cosine, we have a cosine, it would open sideways, and then it would switch over to the other side, still opening sideways. Okay? There's this movie, what's it called? Armageddon. Did you guys watch that? They're trying to get onto an asteroid that was coming to hit the Earth, and so they wanted to land on the asteroid and blow it up so that it won't hit the Earth. And so they did this maneuver where they need to pick up a lot of speed to go. So what they did is they go around the moon, and they pick up speed to try to go catch up to the asteroid. So at that point, when they have to pick up speed, they have to break the orbit so that they don't start spinning around the moon. They have to go fast enough. And to be able to go fast enough, what they did is they essentially wrapped around the moon through a parabolic path, and then to get out of the orbit of the moon, they have to go fast enough, and so they followed a path that looks like this. I mean, if it was real. What? Yeah.
We do the same thing in The Martian.
In The Martian? I have to watch that. I haven't watched that movie yet. All right, let me fix D over here, and D is equal to -1. Let's go to -1. Let me fix D and start changing the eccentricity E. I can't use E because E is like the natural number here. So let's call it A. Oops. We want, what's an ellipse? Ellipse has to be between, what's eccentricity for an ellipse? Less than 1. So let's go from 0 to 1. So here are examples of ellipses with a fixed directrix. Their directrix is at -1. And when we have a small value for your ellipse or for your eccentricity, like 0.2, we have a shape that it almost looks like a circle. And as we get that larger and larger, your eccentricity kind of stretches the ellipse. So what do you think will happen if we go past 1, or if we go to 1? Remember, the eccentricity is 1. What's going to happen? It'll turn into a parabola. So as this thing gets larger and larger, it'll eventually open up and become a parabola. Now, it's hard to see this, but let me see if I can zoom out. So that's 0.99. And then there's only one step after that where it becomes 1 already, so that just breaks off and becomes a parabola. When it goes past 1, what happens? It becomes a hyperbola. So what's cool about this is that if you follow some sort of pattern here, and if you go past 1, you get to that. You get this ellipse that's getting bigger and bigger, and then breaks off and becomes a parabola. And after it becomes a parabola, it starts having images on the other side. And then now you have a hyperbola. And then the hyperbola gets worked out on the other side as well. Okay? So I think in general, I don't know what kind of problems. I have to look at the kind of problems I gave you guys for homework. But in general, I like to stick with an ellipse that's described with a cosine that's going sideways. But we'll see what kind of problems we have in the homework. Any questions so far? I don't know if any of these pictures are going to get to our notes because it's kind of dynamic. Do you guys how many got this program? Graphic calculator program? Giovanni, you have a question?
Yeah, I was kind of wondering about the parabolas where the directrix is sort of like.
Oh, what directrix is on the other side of the focus point?
Right. Like, is that?
I think that's just playing around with a negative sign. I think.
You have like problems where you have to calculate.
I think in that case, what they want you to do is make your appropriate choice for your polar equation, because your polar equation comes in one of these forms. There's a sine or a cosine, and there's a plus or a minus. So I think in those cases, you just want to throw a negative sign so that it's on the opposite side.
Well, one thing is when you turn the negative sign, it's like it moves the focus, so it isn't stuck at 0, 0. So since it's flipped, the focus is above it, so you can actually make an equation.
Oh, so yeah, but that's not the actual focus point that was defined in when we first talked about parabolas. So that's kind of a weird way to approach it. So the key thing is that you can't just kind of blindly choose one of these functions and then plug the values in. You have to, maybe put it in, graph it, and see how it looks like, and then how that's going to change. All right. I started a fake class so that we can take a look at problems, but I don't think I finished working on that. So maybe we'll just dive into your actual homework set and see. And I believe this is section 10.5, 10.6. Yeah, labs are due tomorrow. Tonight. 11:59. So let's see. So write a polar equation. Let's do number 2 here. Write a polar equation of an ellipse. And then we want a vertex at 1 comma pi over 2. So you kind of have to be careful about reading this. 1 comma pi over 2 looks like it's a weird point somewhere, but it looks like it's given in polar form. So this is an r and theta value instead of an x and a y. And if you really look at that, where is that 1 comma pi over 2 point supposed to be in terms of Cartesian coordinate points? What is it? What?
Would it be on Cartesian be
0, 1? So I'm at pi over 2. I'm going right here. And then 1 unit up. Yeah, 0, 1. So write a polar equation of conic with a focus at the origin. So your focus at the origin, and then this is one of the points, one of the vertices. So we can kind of assume that this is a vertex in on the major axis. So we can assume that we have an ellipse that goes down this way, where this is a focus, and this is one of the vertices. Which means our directrix should be up here somewhere, right? So our directrix should be over here somewhere. Now the thing to do is to try to find that equation, because based on our polar coordinate form, we have our eccentricity E is given. And then this is going to go sideways. Our major axis is along the y, so I think we're going to have to use sine theta. And so we have our eccentricity. We just need to figure out what our d is going to equal to. So how do you suppose we're going to be able to find d? What? Isolate, but we don't. We could find d here, but I think I'm more interested in finding d based on the picture. We have the focus point at 0, that's f, and we have the line L. And according to the definition of the eccentricity, remember the definition of eccentricity? What was the definition of eccentricity?
It's the ratio between the distance between the focus point, the vertex, and the
So between the focus point, which one's on top? The focus point, the distance between the point and the focus, and then the point and the line, right? And we do have one particular point right here, and x is equal to 0. That's a nice, easy way to deal with this. So a point is equal to 0, 0, and x is equal to 0 all along these three things that we're trying to, these 3 points that we're trying to find distances between. So we'll just look at the y values. So the point to the focus, what's the distance between the point to the focus? That's 1. And then the point between, the distance between the point and our line, that's the one that's unknown, right? So let's call this distance A for now, and let's solve for A. Eccentricity, they gave us the eccentricity. So the A should be equal to what? One over 0.8? What's 1 over 0.8? 1.25. So looks like our A is 1.25. Is that our directrix D? Is it? What's our directrix D? What is it? (9/4) or add 1 to your A, right? Because this is a distance of 1, and this is a distance of a that we just found that should have a ratio of whatever the eccentricity is. And then you just find that total distance. Okay? So I think if we put those in and then just decide whether we have a plus or a minus, we should get our polar coordinate graph. Sorry, jumping around here. So R is equal to E is 0.8, and our directrix we found out to be 9/4. Let's just use 2.25. And then we want to divide that by 1 plus 0.8, our E again, and then sine theta. So let's see if this thing will end up being the ellipse that we're looking for. That looks about right. And if we trace this, we'll see that the angle is 1.5708, which is pi over 2. Our x and y value are 0 and 1, and our radial distance is 1. So this r comma theta on the left-hand side there, I don't know if you guys can see it, gives you your polar coordinate points. So we found this is your 1 comma pi over 2 polar coordinate points. This is your vertex. This is your focus. And then I didn't draw the I didn't make room for the directrix, but the directrix is up here somewhere. Okay. And if we want, we can also make this into or into parametric equations if we want to trace this out somehow, some way. Okay, any questions? So I guess the tricky part is trying to figure out your directrix to fill in your equation, and that you can get from here. Oh, we should check if it's right. It's right. It should be okay. Trust me? Oh, that's wrong.
You're going to trust us with the quiz.
No. No, you shouldn't trust me. I get things wrong all the time. Okay, any questions about this? So I wanted to see if we can follow the path of the Earth around the Sun by drawing out a thing. Maybe that should be a special assignment for you guys. For everybody. Or what if I make it extra credit? To come up with an equation.
You just draw it.
Okay, this actually can come in different levels. So one extra credit point for your test would be to come up with an equation. So we're going to let the sun be the origin. And then the path of the Earth is an ellipse. Let's make the major axis just along the x-axis. And it doesn't matter if it's on the x positive side or negative side. So what you need to find is the eccentricity. This is a lot for 1 point.
Make it half the
No. So find the eccentricity, and if you do Wolfram alpha and say eccentricity of the Earth with respect to the sun or something like that, they might give it to you, or you can probably Wikipedia or Google it. Find the eccentricity. Of course, you want to find the distance between the sun and the Earth. And in terms of finding the distance, you know, the distance between the Earth and the sun isn't always the same. So you figure out what the maximum is, the minimum, and then from there work out, you know, how are you going to put in your major axis. And once you find that, you essentially have the vertex for your problem. Then you can figure out, using the eccentricity, you can figure out the directrix. And your directrix will be in terms of putting it this way, along the horizontal axis is your major axis. Your directrix is going to be an x is equal to something value. Make things a little bit easier. So you can go x is equal to some negative number, which will make your path around the sun on the left side of your, or you can make your x a negative number, your directrix a negative number, and then your path will be on the positive side. And then find the equation. Find the polar equation of the path of the Earth. Okay? And then graph it to see if it makes sense. Make sure it doesn't look like a hyperbola or something like that. It should be an ellipse going around the sun. And graph. So all this for 1 point, if you want to have fun with it. If not, you know, don't worry about it. Just do your homework, stuff that's due. Okay? Thursday? What's today? Tuesday, Thursday. I want it by Thursday because there's more to this. Because I would be interested in changing this into a parametric equation so I can actually do the parameterization. So we can make the sun go around, we can make the Earth go around the sun in 365 days, or 365.4 or 0.25 days around the Earth. And so we can actually map this using parametric form. So that's why I want it sooner than later. I actually want it tomorrow, but I'll have it due on Thursday. All right, see you guys tomorrow.